Hi, this is lecture 6, which discusses combinational circuit. And in this lecture, what we will do is that we are going to discuss complementary P N and P networks, complex gates, pass transistors, tri-states, and multiplexers, and other topics as well, and other circuit families as well. Um, let's go to the whiteboard here, and then basically we'll talk about the very first um, circuits. But before that, in this lecture, which is uh, lecture lecture 6, circuit families. Basically, we will talk about complementary CMOS circuit, complementary CMOS. We will discuss complex gates, and we'll talk about as well um, about pass transistor, transmission gate, and we will discuss tri-states, uh, and at the end of the chapter, we will look at other circuit families. Um, for example, pseudo-NMOS, dynamic, domino, etc. Okay, so let's start with the very first thing, which is complementary CMOS. All right. What do we mean by that? These type of circuits, complementary CMOS, they are in general they include two networks: a PMOS network and an NMOS network. Okay, this is exactly, I'm drawing the skeleton here. On top, we have here the power supply. On the bottom, we have here ground and inputs to both the PMOS and the NMOS network. Okay, so these are the inputs, and then the output is taken. Oops, sorry. Oops, the output is taken right from the middle here. This is where the output is. Okay. Now, in these circuits, for CMOS to work appropriately, we have either the NMOS or the PMOS should be on. And so we'll refer to this as this is the pull up tree, and this is the pull down uh, tree, and this is pull up because it pulls the output to VD to a value of VDD, and basically charges the output to a value of VDD and becomes logic 1, and pull down because it pulls the output to 0 volt, and the output becomes 0. So we have really, if we look at the pull up and pull down, we have really a so this is my pull up, okay, and this is my pull down, and the pull up and pull down, they have two cases for every one of them. The pull up can be either off or on. What do we mean off? It means there is no path from the output. Let me use another color here. Off means there is no path from the output to VDD. Somehow all there is no path. And if there is a path from VDD to the output, then we say that the pull up is on. Similarly, the pull down can be off and it can be on. Again, what's the definition of on? It means that I have a path from the output to the ground, and in this case I say that the pull down path is on. Otherwise, if there is no path, I'll say it is off. Now, in this case, you see that I have here four quadrants in my table here. Most of CMOS circuits, we would like to have either the pull up or the pull down on one of them is on and the other is off. So if you look at this case here, you will see that the pull-up is on and the pull-down is off. And this is when I will have the output equals to logic 1. Okay, the output will be charged to VDD. And in this quadrant here, that the output, the pull-up is off and the pull-down is on, this is where I'll have the output value equals 0, logic 0, 0 volt, logic 0. Okay, all right, what about the two other quadrants? What happens if I have both the pull-up and the pull-down are off? And in this case, what happened, I'm going to call the output here is floating or high impedance. What do we mean by floating or high impedance? When the output node here does not have a direct path to power supply or to ground, then this node is referred to it electrically as floating, because it could have a value between 0 volt all the way to VDD. We are not sure. And we have another term for that. We call it, it's high impedance. It is as if it is separated from the power supply or ground with a very high or an infinite impedance or resistance. This is typically a case where in the circuits we try to avoid. However, in some cases we design circuits to have their output high impedance, and we will look at those circuits, very limited cases. Okay, and then what about when both the pull up and the pull down are on? And we get into this case where we say that we are short circuiting the VDD to the ground. And this is the case where we call that this is a crowbar and a current, and this is where the case we try to avoid in CMOS, because CMOS is supposed to be minimal power dissipation, and in this case dissipates power unnecessarily because the output is not determined. I'm wasting my power, and basically what it means, I was not careful in designing my gates. Okay, so let's try to explain some of the CMOS circuits here, complementary CMOS circuits, and then we'll try to get into some. Okay, so we'll look at the implementation of Nand Gate, okay, and then NOR gate, then complex gates. Okay, so a NAND gate, let's draw the symbol here. This is A, B, and here is the Y output. The truth table for the NAND gate is A, B, is Y, and see low, 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 high, high, low, high, high, and the output is um, high, 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 low. Okay, so in terms of the implementation, we can construct it as such. This is the series of NMOS implies, again I repeat, the series of NMOS devices implies the AND logic. So here is A and B. Okay, so once we construct the NMOS, we go to the PMOS, and whatever in series becomes parallel and vice versa. So here we have the NMOS in series, the PMOS are in parallel. So here's the PMOS, power supply, and here's the PMOS power supply. Okay, so this is the construction of notice again my earlier comment, which is the following. This series implies ending logic. Okay, and whatever we do in the NMOS, we do the opposite in the PMOS. Let's take, for example, the NOR gate. Okay, so this is the NOR gate, A, B, Y here as well, and the truth table, A, B, Y. Let's see if I can get, okay, so low, 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 high, high, low, high, high, and obviously the output is high when both are lows and the rest are low, low, low. Now, um, the way we construct the gate is, again, the logic. We start with the logic. It implies with the NMOS gates better than the PMOS. So we say that, okay, so we want to draw this gate. We have an O-ring, and the O-ring implies parallel of an NMOS. So here is A and here is B. Okay, this is parallel for the NMOS. Now, whatever next step, so this is the output here. Next step, whatever parallel in the NMOS becomes series in the PMOS. So the PMOS subtree is like this. A, this is B. Now, let's try to examine those a little better. Okay, so let's go back here to the NMOS. The question here, how is this output is high here? Why it is high? Well, the output is high here because whenever one of these inputs is low, one of them is low, then one of those transistors it will be off, cutting the path from the output to the ground. Okay, so and if one of the inputs is low, then one of these PMOSes will be on, and that provides a path from the VDD all the way to the output, and thereby charging the output to VDD logic 1. Okay, and that's what we are seeing here. Okay, and there is one case where uh, when both of these guys are high, let's just choose another color here. When both of these guys are high, okay, so when this is high, this is high, okay, then this is becomes both of them are on, providing a path to the ground. This is where we see the low right here. Take this similar analysis to the NOR gate, and in the NOR gate we say that when one of the inputs is high, the A or the B, it makes the NMOS on, providing a path to the ground. Notice that when one of the input is high, one of these PMOSes will be off, cutting the path between the output to the power supply. And in this case, we have when one of the inputs is high, we have a path to the ground and no path to the power supply. That explains why you have a low output here. Now, when both inputs are low, so this is low, this is low. Okay, well, let's change color here. When this is low and this is low, so this is on, and both of these will be off. And in this case, we don't have path from the output to the ground. Rather, we have a path coming from the power supply to the output. This charges the output to high, and that explains why we have a high here. Okay, all right. So the other point that we want to add here, well, what happened instead of two input NAND gates, I have a three input NAND gates. Okay, meaning I am increasing the inputs instead of AB, let's make it ABC. Can I use the same structure? Absolutely. All what you need to add is just add a one transistor here in this series, connect it to C, and one parallel here, and connect this to C, PMOS to C. And here you have three input NAND gate. Okay, and similarly, what happens if I have 3-input NOR gate? A, B, C, and I can use the same drawing. Absolutely, I can add the C here as a PMOS and then connect it to the power. So this is C, and I can have one more transistor here in MOS, and I connect this to the C, and here is we have 3-input NOR gates. You can extrapolate on this to other inputs, 4 inputs, 5 inputs, 6 inputs of NAND and NOR gates. Okay, so with this discussion, let's talk about how can I have a complex gate using complementary CMOS. Now we are talking about complex gates using complementary. For example, suppose I have a function which says y. I need to design a function which says y a b, okay, plus c d prime. Okay. Well, the very first thing we do here is that in these type of gates, complex gates, um, the steps that we follow is the following. Okay, the first thing is we will start always with the MOS subtree, and as we learned before, ANDing means series of MOS. ORing means parallel of MOS. Okay, once we construct the MOS subtree, then I construct the PMOS subtree. And the PMOS subtree, whatever is in the MOS series, I make it parallel. And whatever parallel in MOS, I make it series. Okay, don't forget that we have the power supply and the ground, and also don't forget the output gets in between the NMOS, the PMOS, and the MMOS. Also, don't forget that the output always inverted. Okay, always inverted. Okay, now taking these hints, tips, and let's go back to our question here, and we want to design this circuit. Okay, which is right here, A B. Now notice that A, there is an AND here, A or CD. So here we have ANDing, and here we have ANDing, and between the two I have an ORing. Okay, so the construction of this circuit is very straightforward. The very first thing we do is that let's construct the NMOS. So I know that I have a power supply, and in between there is the output, and then I have a ground. This is where the PMOS circuit is, and this is where the NMOS circuit is. Okay, and in the NMOS, what I have here is that I have an ANDing of A and B. Okay, so let's see here, an ANDing of two transistor A and B, and an ANDing of C and D, C and D, C and D. Both these subtrees are in parallel. Why? Because I have an OR here. So I connect them in parallel. On top is the output. On bottom here I have the ground. Now let's go to the PMOS subtree. And the PMOS subtree here, I can construct it by taking care of whatever series becomes parallel. So there is a parallel, this one is in parallel with this, right? Then this becomes in series of this. Something is in series. Okay, inside this one here, I have A and B are in what? I have them in series. They become in parallel. So now you can see that I have A, B, okay, right? They are in parallel, okay, and then they are in series of what? See, notice CD here, CD here. This is the CD stuff here. CD, they are in series, they become in parallel. This is C, this is D. Okay, so this is parallel, and this is my circuit right here. So notice that the output, the ground, okay, they are all there. Okay, the inputs are connected. This is A, I forgot probably B here. Okay, all my input, my inputs and transistors are connected appropriately. Okay, let's take another example. Another example. Let's take another example. Suppose, for example, I want to design this circuit. Y equals A or B or C ended with B prime. Okay, same steps, don't change. Same steps, they don't change. Okay, notice the prime here. Okay, first of all, let's start with the MOS. MOS subtree. What do I have here? I have O-ring. Okay, I have ANDing here, then followed by an ANDing. And so I have something in parallel, something in parallel, something in parallel. Okay, so this is what? This is A and B and C. They are in parallel. Okay, they are in series of what? They are in series with D. Okay, okay, so this is the subtree. Okay, now I know the subtree at the bottom, they have to be a ground. On top, there have to be the output Y. Now then comes what? Then comes the PMOS. The PMOS, we start here, okay, with the PMOS. We start here on top, we have a power supply. And then whatever here in series becomes parallel. Oh, this is connected here. Whatever here in series becomes parallel. So you have here D in parallel with something. What is that something? Well, it is A, B, C. They are in parallel, they become in series. A, B, C. Okay, C. And then I connect the PMOS tree to the output. Okay, what happened if he gives me this problem where it says without the prime. Let's say, for example, here he says I need Z where A or B or C ANDed with D. There is no prime here. There is no prime. The output is not prime. In this case, what do I need? I have to add an inverter. Okay, invert the output. And in this case, the output here becomes, this is the correct output Z. So this is right here, the Z. Okay, all right. Okay, so these are the steps. As we said, we draw the NMOS subtree. Okay, then the PMOS subtree, connect the power, ground, output. Okay, and all the inputs correctly. And when you construct the NMOS subtree, whatever ANDing becomes series, whatever ORing parallel, and then the PMOS you make everything opposite you created in the MOS. Whatever series is parallel, whatever parallel is series. This is how you construct compound complex gates using complementary CMOS. Okay, now one thing here we are going to move to another family of circuits, and one of those families is called pass transistor family. And pass transistor consists of a transistor, and we take the output from here. Okay, so this is, for example, uh, let's say A, and this is S. The value of Y becomes A ANDed. Oops, did I say? Okay, so let's say A, S. This is Y, and Y is A ANDed with S. Okay. Um, it is important that we realize that um, when the output here is high, then the charging through the PMOS, we will charge the output Y to VDD minus threshold. Why? Because as we discussed earlier, the NMOS is a bad charger. It doesn't charge all the way to VDD. It will shut off once it passes VDD minus VT. Once the Y increases a little bit above VDD minus VT, the NMOS becomes off. Okay, now, so the maximum capacity we can do is up to VDD minus VT. Okay, so what's the solution now? Well, the solution is that we use the transmission gate. The transmission gate, where I have an NMOS, okay, as I have before. This is A, this is S, and a PMOS transistor connected to it in parallel and controlled by S prime. And in this case, Y has the same functionality, but here, when I charge this node to VDD, it will go to all the way to VDD and no restriction of VDD minus VT. So notice that the difference here, that here we charge VDD minus VT. It's a weak one. And here we charge all the way to VDD, which is the appropriate one. Obviously, as you know, that not going all the way to VDD affects many things, including noise margin. So this is bad for noise margin. Okay. Um, so not going. So that's why transmit. But here, what did we have to pay here extra? We paid extra transistor here. Okay. So this is the transmission gate that we have here, and um, in we can extrapolate in this concept here and say, okay, let's try and study this last configuration a little better. So we have here our NMOS, okay, and our PMOS here, okay, and let's use enable line here, and this is enable prime, and this is the input A, and this is the input Y. The behavior of this gate can be accurately described in this table, because before, when we said it's an ANDing, we were not very accurate. The most accurate description is to say when the enable 0 or 1, there are two cases here. Okay, so when the enable is 0, okay, notice we are shutting off both transistor, and the output now is completely disconnected, and we say that it has a Z value. But when the enable is 1, now we can pass both the NMOS and the PMOS are on, and we can pass the value of A all the way to Y, and we say that Y equals the value of A. Okay, and in fact, we call it non-restoring a tri-state circuit. Non-restoring tri-state circuit. Let's understand what's non-restore. Non-restoring, it means whatever value power, strength power of the signal A is being passed to Y. So typically in circuits, we don't like non-restoring because any noise in A will be copied to Y. Okay, but anyway, very small tri-state circuit, and the logic symbol for this circuit is like so. Okay, so this is A, Y, and here is and the control. Sometimes we add another line at the bottom, but this is the tri-state symbol. There is no bubble here, by the way. Okay. Now we have restoring tri-state, and restoring tri-state is the following. Um, you we can say that it has this following structure. Okay, so this is my input A. Okay, and we have the control signals here. Right here you have This is the enable bar, and this is the enable here. Okay, how does the circuit work? Okay, so this is A, this is B. The circuit works as follows. Okay, here is enable, here is the output. The enable either 0 or 1. If the enable is 0, it will disconnect the output, which is, whoops, this should be Y here, the output from power and ground, and this is becomes a high impedance. But if the enable is 1, then Y equals A prime. It becomes like an inverter circuit. And in fact, we can have this the logical symbol of this is like so. So we call it a tri-state. And in many cases, when people say tri-state, they mean actually the restoring tri-state. Okay, we'll stop here and we'll continue our discussion in the next part of this lecture. Thank you.